a lot of speakers already talked about things that I want to say to some extent, so hopefully this will speed up a little bit what I want to say. But on the other hand, I also want to not miss my message here. So, as it did automatically here, the starting point of dynamical systems, from my point of view, is deterministic dynamical systems, and there's a lot of good things come out of it. So, what is bifurcation in my terms? Is some kind of qualitative change in dynamics if parameters are varied. This is a vague notion. It's not a precise mathematical definition, but I think it suits very well if you look at all the type of bifurcation that people have seen. So whenever you fix some notion of bifurcation, you usually get into trouble at some point or another. Good, so what are the important things that have been done? Singularity theories played a big role, maybe first in phase transition theories or Landau theory, but later just in reducing some kind of bifurcation problems, say from equilibria periodic solutions, so to effectively some zeros of smooth functions, and this has been very, very useful. Then there's a whole basically algebraic theory in some sense how to do this. And another class of problems very important is homoclinic bifurcations, which are basically at the heart of going from basically orderly behavior to disordered behavior or chaotic dynamics. So there's some kind of a reasonably well-established body of theory. It's not perfect, and there is and this forms a basis for the qualitative theory of dynamical systems in some sense. Yeah, there's some notes I can make about this. I don't think actually somehow that this theory is anywhere close to completion, but at least there's a reasonable body of work, and people know what you mean if you talk about bifurcation theory. So I'm going to talk about dynamical systems with noise, or something like that, and so there's some kind of like arguments for why I think it's interesting. I started many years ago thinking about these things. Why? Because people come and knock on my door and say, like, can you help me with something? And then invariably they have some kind of dynamical system with noise. And for instance, bifurcation, there seems to be very little known. So people see a lot of things on computers, they simulate lots of stuff, and the question is like, what can you do? So of course, we can think of sources of noise. Either we really have a system which is driven by some signal, and I seem to know probabilistic characterization of the signal, but maybe not exactly the signal somehow. So this is some kind of special type of non-autonomous dynamics. So in some sense, random systems from this point of view are a bit easier than general non-autonomous dynamics because I know something about the driving signal. It's not arbitrary. And Sanjay also mentioned something about this. I'll keep doing this. Another reason is that high-dimensional systems may admit a reduction to a low-dimensional system driven by noise, where noise somehow reflects on the ignored degrees of freedom somehow. So this is another kind of important source of noise potentially, and I will hope to say something about that later. And another thing which is a good argument to consider systems with noise is that when we write down equations of motion, we may not really know what the equations of motion really are. So there's some kind of like mathematical theory that says if we know the equation of motion, then we can study a lot of properties. But what if we just really don't know what they are? And so there's all kind of different approaches to look at some kind of generic equations or what that has a lot of problems. So one way around it is I'll say, well, why not fluctuate your equation of motion if you don't know it so precisely? So what you actually effectively do with noise, you could actually wipe out a little bit of the detail by adding noise somehow. Of course, the question is like, does it then become easier or does it become harder? And well, sometimes it becomes easier. Yeah, so sometimes noise helps you to obtain certain results that maybe in a deterministic setting, because there's so much detail, you can't really obtain.
But it also depends on whether you inject noise into variables, right, or into parameters.
Sure. I'm just making a general statement here. Okay. Yeah. I'm not doing politics here yet.
Expecting that.
Not yet. Okay. But, so some examples. So one's kind of Thiago's example. Dynamics in hubs where you have some kind of mean field and then there's some mistake, maybe, and this mistake is fluctuations. You can either argue that you have so many particles that somehow these fluctuations are almost zero, so you don't care. But you could actually also work in a regime where these fluctuations are considerable and they're important. And some other aspects, stochastic climate dynamics, been a lot of papers about these things, and there's also some interest maybe in modeling of complicated systems where you don't really know the equation of motion at all. And maybe if you do fitting, you could fit with any kind of model, maybe deterministic model, but maybe also with a random dynamical system. So I think that's actually a very promising idea to kind of obtain for complex systems a good reduced model, but not looking for a deterministic model. Okay, so I'm going to look at two types of random dynamical systems. I don't want to pin myself down too much. Also, this talk is going to be really low-key on technicalities. This is not a reflection of what I usually do, but it's just because I think somehow I'm tired and the meeting is tired, and so I'm going to just try to talk phenomenology rather than details. There's a lot of details, though, in a lot of things that we've done. So there will be references. But the two types of system. One is stochastic differential equation. Here's some canonical type of equation. Don't make it too complicated. It's just some kind of additive noise. And here's some kind of like mapping. You can think of a time-bound mapping, whereas we also have some additive noise. So these are the kind of prototypical systems I will talk about. It's not necessarily that it's that we have to be constrained to that, but I just do it here. So what's important, I think, here is that these noises are diffusive in some sense. So if you have noise which is not diffusive, it just gets more complicated, usually. But if you have diffusive noise, then in some sense you spread things around, and this actually helps you understanding things. So I think also it's important observation somehow. Okay, so let me just first review a few noise-induced phenomena in the literature, just as some potpourri of what's been there in the past. And there's some references here, and some people here know very well about that. Just to get some overview. So for the noise-induced order, this is something which sounds maybe a little bit strange. So you have something which is chaotic, you add a little bit of noise, and suddenly it becomes more or less not so chaotic. So the Lyapunov exponent goes from positive to negative after adding some noise. If you think about it, you say, why not? But there's an interesting observation here, Matsumoto Tsuda in 1983, and it was only basically made rigorous very recently by Carlatolo and others using interval arithmetic and exact computation, so computer-assisted proof. That's interesting type of phenomena, but it just shows that lots of things can happen if you add noise. We have also noise-induced chaos. Here's an example of a Henon map where we have a periodic 7 orbit. In the background, there's some kind of unstable set. If we add some noise, some critical value, suddenly you see a Henon attractor that wasn't there before. It's just there because the noise gives you accessibility. Yeah. And another noise-induced phenomena is noise-induced synchronization. So here you see two particles in the same dynamical system, and what happens is they go close to each other. It happens very quickly. So, okay, maybe I should just let it run. Okay. So what happens, you have two initial conditions, and what happens just experimentally, I see here, just explanation, I see these particles. Why happens if double well, if you push two particles in the same well, they end up close to each other. And yeah.
It's common noise, right? So basically it's two.
Yeah, two particles in the same system. Two particles in the same system, common noise. That's right, it's essential, of course. Yeah. Sorry, this keeps flipping here. Stochastic resonance, that's I think the phenomenon in dynamics with noise, which is most famous in science. So you have tens of thousands of references to stochastic resonance. And so what's the idea is that there's some kind of critical value of noise by which if you have a periodic signal in the background and you add some noise, that basically you get this amplified in some sense. So you get amplification of periodic signal. So I think there's actually quite a lot of things still to be understood in terms of dynamics here. So there's some very simple toy models like two-state model where you can see things, and there's some numerics on these kind of things, but it's quite a lot of things to be understood there still actually. So it's an interesting problem. Another thing where people talk a lot about is this kind of transitions where you just jump, some first order transition where you jump in some state and we have some noise and you see fluctuations, and maybe on the size of the fluctuation you can see if you're close to a bifurcation point. So Martin Schäfer's made a big deal out of that, critical decisions in society and nature and so on and so on. Yeah. Good. So there's a couple of different approaches to random dynamical systems, and I'd like to just, Sandro talked a little bit about this, so let me just be brief. So one is, what's my favorite one, is to think of RDS, random dynamical system, as Q product. So we have some signal that drives something else, but there's no coupling back. So there's something independent that drives it, and it has some probabilistic properties. Yeah, so we call this Q product because we have this kind of one-way direction. The signal drives the system, but the system doesn't couple back to the signal. And then we assume some probabilistic properties of the signal. And the simplest one is where we have some kind of like IID type of noise realizations, for instance, additive noise. And we can think of noise realization as being basically a whole sequence of this. So there's values that we add, and then we can put some probability measure on this and so on, and you get some random dynamical system in some sense. So what the idea is that we actually not look at just the dynamics of the random system where the noise is some nothing. Now the noise is part of the dynamics. The noise actually evolves, and we can ask about what is the dynamics as a function of noise realization. Yeah, and then of course the game is somehow to get some results of maybe some things hold for almost all noise realizations. That's the ideal, or for a very large measure set of noise realizations. Okay, you can also do this with SDEs. It's not intrinsic in the formulation of SDEs that there is a skew product, but if you work hard, then like in Arnold's book, you can see that you can do this. So the idea is basically that you have some kind of like noise realization with your continuous functions, and they're almost surely rough if you equip this function space with the Wiener measure. And so and then you have basically a complicated differential equation because the driving signal is not smooth, and then you have to do some kind of like intelligent integration conventions and so on. Yeah, I will not really, but it's about just one example. Famous example, of course, of random dynamical system is also SDE, because you can think of it as also skew product. Good. Now there's different ways now to think about this dynamical system. So a very popular one is to basically look at this propagation of measures, and I call this the one-point Markov process. So why do I call it one-point process? Because I want to make a point, 1 point. And the point is that basically this actually models as a Markov process orbits of the system. So it gives a probabilistic description of some process that actually generates orbits. But it has less information than principal skew product formulation, because skew product formulation can ask all kinds of questions like how do many different initial conditions evolve at the same time under the system, whereas in the Markov thing you don't have this. You can only have properties of one equation. So for instance, you cannot really ask the question how likely is it if you start with two initial conditions close to each other, how often they come close back to each other. This is impossible to answer from this Markov chain point of view, unless you then, if you write different equation of motion, the Markov chain for the two-point process, for instance. So these things are well documented in the literature, but very few people seem to have worked on them. So it's something I want to point out. Of course, and then what do we do with these Markov processes? So usually we look for invariant measures of a certain kind, and then we hope to use ecodicity, because ecodicity tells us that the measures tell us something about certain averages that we may be interested, but maybe also not. So another warning sign I would say that just getting lots of invariant measures doesn't necessarily mean that we actually get to understand what we really, the questions, answer to the questions. So I think before you start doing all this stuff, you should maybe ask what is the question you have. Okay, third point, the final point on the philosophy is like nature of the noise. So there's all kind of models of noise. Of course, this is kind of Brownian motion, which is very popular. And for some reason or another, I'm not a big fan of Brownian motion in general, because I think it has very special properties. And these very special properties may have an effect on your dynamics that you're not aware of. So you may think this is some generic noise, but it's maybe not. It has maybe special properties. Now, one interesting alternative to Brownian motion in some sense is bounded noise. And bounded noise, I mean that basically you cannot really, in an arbitrarily small time step, reach everywhere in the phase space. Let me just finish this. And what is the advantage of such a model with bounded noise is that you get trapping regions. You may actually be confined to a certain part of the phase space, and then maybe the transition where you suddenly can go somewhere else. So if you have unbounded noise, you can always go everywhere. You may say, well, sorry, this just keeps flipping here. You may say, well, but it's a very small chance to go somewhere else. The problem is if you now go to time to infinity, then of course almost surely this happens. So very unlikely things happen almost surely if you go to time to infinity. So that's not such a good idea sometimes for the noise. So there's two reasons, I think, where you might be interested in bounded noise. Either the noise is really bounded. I think there's many applications where the noise effectively is bounded. Or maybe it's essentially bounded because I'm really interested in a certain time scale for the model, so I'm not really interested in very, very rare fluctuations to take them into account. Yeah. So there's these arguments. Sorry, your question.
Well, yeah, I was just going to ask if you could expand a little bit on your comment about the special properties of Brownian motion, because I remember in a class, listing the special properties of Brownian motion, but then looking and saying, okay, if you transform it in this way, you transform it in that way, you get all sorts of other processes. So I was under the impression that Brownian motion was sort of based.
Well, you have independent increments. This is, of course, the first thing, which is really very special. And this also gives rise to some dynamical properties. For instance, the statistical properties, for instance, the two-point motion in Brownian motion, the different processes invokes all the endpoint motions somehow. So all the endpoint motions are actually basically a function of the 2-point motion. This is a result by Kognita. And this is not true in general. So there's a richer dynamics in some sense in general random dynamical system than there is there in some kind of something driven by boundary motion.
I see, and so you wouldn't consider it a sort of base case that then you...
Oh yeah, why not? But you have to just understand that it's not a generic noise. There may be good reasons why you think that your system, your noise that you have to consider is Brownian motion. There's sometimes very good reasons to do that, but I wouldn't say that you have to just by default should assume that it's Brownian motion. Challenge is like, who gives me data that they can show that more or less Brownian motion assumptions are satisfied. Sorry, this thing keeps flipping by itself. Yeah. Okay, so what I'm going to do now is I'm going to walk through a certain number of not arbitrary examples that I've looked at, and try to kind of basically make a potpourri of results, and hopefully this stimulates the thought and message in some sense is that there are interesting things happening in random dynamical systems that maybe you didn't think about, and even in systems that are relatively simple. And so there's lots of opportunity to do interesting things there. And that's how we can. But that's both on the applied side, I would say, but also on the theoretical side, so not a lot of problems. Good, so pitchfork bifurcation with additive noise. So think of this very canonical one-dimensional SDE, which is like textbook example, some kind of potential. We have a parameter, we either have a single bell or a double bell potential, and I'm just looking at this kind of additive Brownian motion. I'm just asking like what happens here. And the example that we just showed in the simulation is precisely this kind of example here on the right. Yeah, so you can do this Markov semi-group. You can do this Markov process, and it's very nice that you can see that the Fokker-Planck equation, which basically describes this evolution of measures, has a fixed point and actually an attracting fixed point. And so we can solve this explicitly actually here. So we get a very nice equation, which is some kind of exponential minus of the potential for this thing. And then we have basically stationary distribution, which is either unimodal or it's bimodal. Yeah. So this find is found in many texts. So you think, okay, that's it. So this looks like a kind of bifurcation because you have a different shape of the distribution. One has to be a little bit careful, I think, with such characterizations, unless it's really meaningful, because of course if you change coordinates, you can create as many local maxima and minima as you like. So this is not really invariant under lots of different transformations, but this is called, Ludwig Arnold called it phenomenological bifurcation. But if you look at the dynamics of trajectories, you see something interesting. If I take different initial conditions of the same system running on the same noise, what you see is that somehow 3 different initials converge to actually one signal, and here also 3 initial conditions to do something different. At some point, they do one signal. So what seems here is that you have this synchronization, noise-induced synchronization in such a system. So this is also well known, but maybe it's interesting. So this doesn't follow at all from this distribution, because the distribution only says that if you follow one trajectory, it gives you some kind of like distribution of where you are. It doesn't say that if you take different initial conditions, they're actually attracted to each other. So how can you analyze this? Well, for instance, one feature which doesn't prove this, but which is remarkable in some sense, you can do a Lyapunov exponent. In this case, is one-dimensional, so it's kind of easy. It's just the average of the derivative. You know the stationary density, so you can just basically take the average, and you can actually see that this integral must be negative. Actually, in general, Lyapunov exponents for one-dimensional SDEs are non-positive, and they are very rarely zero. So there must be very special properties for them to be zero. So in some sense, in one-dimensional SDEs, they usually have the synchronizing behavior, and not much else is going on. Now, one way of looking at these trajectories is from kind of like pullback dynamics. Why? Because there's a problem. If you look at trajectories that are driven by some random signal, they will usually not converge somehow, because they will behave depending on what the noise does in the future. But if you actually basically look at the dynamics which is starting in the past, and then running it forward, and then more in the past and more in the past on a fixed noise realization, in some sense the effect of the far past becomes less and less, and you get the opportunity that things converge. So often they do converge, and so kind of results about that when these things converge. And then we just need to kind of look at 2 sides at a time. So we must make sure that we know something of the past of the noise realization, but then you can actually have objects that mean something. Yeah, so that's one way to kind of get some mathematical results here, because otherwise, objects just fly away all the time. Okay, so this is some slide which says something that Sandro already said. Basically, we have kind of a stationary measure, and we can look at disintegration of stationary measure with respect to noise realization, and particularly with respect to this pullback things, and we call this Markov measures. So we have some kind of measures that describe so-called pullback attractors or statistical behavior depending on the noise realization, and they evolve under the dynamics, like which Sandro called equivariance. I would just call just evolves over the fibers. And this for me is an invariant measure of the skew product. And if you look at the marginal, then this is an invariant measure of the Markov process associated to that. Good. And then there's some properties you can see from this. I don't really want to spend too much time on this. So what's interesting is that we have this random fixed point. We have some kind of, if you now look at the pullback attractor, if you start in the past, then actually, and this idea that all these attractors converge will mean that actually we have a well-defined point on this fiber, on this measure, and here this is the definition. So we have some kind of delta measure, which is basically the pullback of actually any initial condition here, but for instance of the stationary measure. So you can actually define these things. So we have now a situation, an attractor, which on each fiber there's just one point. So if I know the noise realization in the past, I know exactly where I am. That's the condition. So that's the kind of the simplest random dynamics that we can have. Is that basically, is that like a fixed point in a deterministic system? Everything converges to one point. If it's random, then it's almost unavoidable that this will behave as a function of the noise. Yeah, so we have this kind of now the question is like, does it now destroy bifurcation? Because, so my talk title had bifurcation, is change of behavior. If I go from single well to double well, I clearly have a bifurcation, a pitchfork bifurcation. You have either one minimum, where you usually tend to sit, or you have two minima, so you can be on the right or on the left. But now if you have this random fixed point, which is unique, then what we have, the situation is that, maybe there's no real bifurcation somehow, because we just converge to a single point, irrespective of the value of alpha, irrespective of the shape of this potential. So there was this paper by Crowell and Flanderly in '98, which basically had the title "Additive Noise Destroys Pitchfork Bifurcation." And the question, like, should it be, or is it like this? And it turns out that it's not quite like that, and it's quite subtle. It's that yes, we have kind of convergence to this random fixed point, but it's not uniform. It depends actually on the noise realization. Well, it depends on the noise realization. The constant here in the exponential convergence situation, this constant is unbounded if you have the double well potential, and it's actually bounded from above by some constant in the single well. So what makes the difference? Well, the difference is that in the single well, I eventually, after some time, everyone converges to the equilibrium, whereas in the double well, it just depends on noise realization. I can avoid converging as long as I want, because I can always go to a region of the phase space where I destabilize, because near the maximum of the potential, I can actually separate trajectory. So I can delay converging as long as I want, but in the end, this has zero probability to keep separating. So I can desynchronize whenever I want, but in the end, the noise realization will have zero measure if I keep doing this forever. So one measure of doing this is so-called using dichotomy spectrum, which is more like a uniform version of this, the IPAM spectrum. The IPAM spectrum is not uniform. It's very important. So it's not the same as eigenvalues of a fixed point, because that's uniform. But actually, the IPAM spectrum is not uniform, so that's important. So in some sense, also this gives some kind of like rise to think about that random systems are very much, in general, like non-uniform hyperbolic systems somehow. This is a typical kind of a feature of non-uniform hyperbolicity. Yeah. Good. So it's also interesting, some of this is a comment, that while we would advocate that you have a bifurcation because of a change of this behavior, but actually you could also show that actually all this random dynamics is topologically randomly conjugate, albeit with a very, very rough conjugacy. If you put some limits on the roughness of the conjugacy, you can't do it anymore. So this is an interesting little things. So one other aspect somehow here is that you can look at finite time diapason exponents. And so if you have this uniform convergence, then all the finite time diapason exponents at some point lie in the negative half line. So the support of the finite time exponents, they're all negative. Whereas if you have this kind of non-uniform hyperbolicity, you have these exponents lying both in the negative and the positive part, and you can't really get rid of them. So if you increase time, then what happens is this distribution of measured exponents becomes very narrow. It becomes like a delta function, but there's always a support, and the support always includes positive values. There's always a positive chance to observe positively Lyapunov exponent in such systems, even though the real Laplace response is negative. But that's really important somehow. It's not a detail. Okay, so how can you see why this happens? Well, here's a picture of two-point motion of the underlying vector field with the potential. So we have three equilibria here on the diagonal. So this x and y of the two particles. So we have stability, we have instability here, stability here. But what happens is that if you're near a stable point, the noise goes in along diagonals in this model. And what happens is you can actually jump from here to here, and then the dynamics can just carry you away. So it's always possible. There's always a possible probability wherever you are to basically desynchronize. And so it's just really inherent in the dynamics. Should be no surprise that this happens.
You are advocating against a Brownian motion. How much what this result depends on the Brownian?
Oh yeah, I know here, of course I take just a simple example. Here the Brownian motion is not really essential. It's not essential. I can take something with bounded noise, some additive bounded noise or some whatever. It will have similar properties. Yeah, there's no aspect here of Brownian motion which is really important. It's just easy because I know that I can calculate stationary measure by hand and some other things.
But getting bounded noise in the differential equation is kind of hard.
No, you can just do random the differential equation. You can just have a term which depends on a random variable and you just feed it like that. It will not have independent increments, but it's still okay. Yeah, no problem. So if you insist on independent increments, then you precisely get Brownian motion. You get also this roughness. So the roughness is a direct consequence of the fact that you insist on independent increments. But is that essential or not? Okay. Shear-induced chaos. So second example. Let me keep an eye on my time. Yeah. So there's some papers here. Sorry, it's a bit small. So there's a paper by Lasseng Yong and Kevin Lin. 2008, shear-induced chaos somehow. And so what happens if we have a limit cycle, which is attracting, and we just add some noise. It could be that the shear is high enough, and some kind of noise induces some kind of chaotic behavior. And that's interesting. So in the one-dimensional case, we said everything basically synchronizes. So I'm now looking at the two-dimensional differential equation. Again, we do Brownian motions so because it just facilitates the computation of certain things. So here, for instance, two-dimensional equation, this has Hopf bifurcation. And the nice thing, again, for this kind of equation, I can write down explicitly what the density is of the stationary measure. Yeah? So this is just, again, some kind of potential formula. And what's interesting now is that there's some parameters here, but this parameter B doesn't appear at all in this density. It turns out that this parameter B just disappears. It's not important. Okay, so we have this kind of thing, and then, yeah. So but you can look at these, the stationary measure. Here's the deterministic dynamics. Some you have a limit cycle, or you have just extracting to an equilibrium point, and here have you the corresponding stationary measure, which either has a maximum around limit cycle or around the equilibrium point. No surprise there. No, but now you can actually look at this, at the dynamics underlying, and I'm looking at this pullback object. I'm looking at basically the dynamics of a group of points. If you do pullback construction, that's basically the underlying dynamics of the system, not average, not the one-point motion. It's just average. So if I look at each of these fibers, if I have synchronization, I just see 1 point. There's a little dot here. It's not a dirty. It's like really, yeah. But with the same distribution, this is for a small shear, B is 1. If I take B is 20, I suddenly get some object looks like a strange attractor.
Maybe you should say that the shear pushes the phase point backwards, so it doesn't go clockwise, but it's a little bit counterclockwise, right?
Yeah, so what the thing is like the speed depends on B, right? So the fact is if you go out, so the shear, what it does, it actually kind of speeds things up or slows things down.
Very little smell close shear.
Yeah. Good. So that's the shear that basically, so the shear is not by itself, well the shear of course leads to some stretching. And it turns out that this noise interacting with the shear somehow does something that actually goes from synchronization, which is the most boring type of random dynamics, to something which looks like some kind of chaotic attractor. Of course, this is a non-autonomous object. You have to fix here some noise realization in some sense. And of course, if you now let the noise go forward, then this object will actually evolve. But in something similar, it will be some kind of moving object of this type. Good. So what's actually very interesting is how chaos appears in a random system. So there's a lot of work on how chaos appears in deterministic systems. For instance, by Andrei's father, Shilnikov. But by many other people as well. And there's a lot of understanding. But here the system is quite different actually. So what you have here, 1 point, And suddenly, you have this thing. There's no in-between. There's just a point, and then there's something which is a non-trivial object of a certain size. This is not first very small, and then it becomes very big. No, it's actually very big immediately. Yeah. So this is something that we are working on, and no real results yet, but it's hard problem somehow, and it's...
And what is noise here? I mean, because I thought that shear attractor, shear induced attractor, it's already something chaotic like this, right? Like it's not just this limit cycle, right? It's
Yeah.
kind of fractal structure, right?
Well, yeah, that looks like something like this.
Yeah.
It's a bit like some kind of...
And the noise even amplifies it even more.
This is what it looks like.
Okay.
Okay, but it's interesting, and it's a problem. So the question is saying roots to chaos was one of the first things that people found interesting in dynamics. Well, roots to chaos in random systems, you say, well, it's the Lyapunov exponent. The Lyapunov exponent is an average quantity that you can try to measure, but it's not something that really you say, where does it come from? Where does it come from that now on average I basically have expansion? And this is a very interesting question, I think. So, good. So yeah, we did some stuff on this and so on, but sometimes you can prove that you have this chaos. Sometimes you can prove that you have positive Lyapunov exponent. That's hard in general in these kind of problems. So for this specific problem, we can't really prove analytically, or there's no proper proof. There's some other systems where we can prove it with some hard work. So these are not so easy problems. Good. Next problem that I want to talk about is bifurcation of trapping regions. So trapping regions are these things where I have bounded noise and I get basically locked up in a certain region. And maybe if the noise changes or some parameters change, I can suddenly kind of behave in a completely different way. So there's some papers here, again. I remember having a discussion with Arkady at some point about bounded noise, whether it makes any sense. I think some people think it makes sense. I can see that in some settings it doesn't make sense, but I think there are settings really where it makes lots of sense, and people also using it, try to use it, but the literature is still very thin in some sense on this. And I remember that talking to Egbert van Ness from Scheffer's group, he's in ecology, and he says, well, if I don't use boundary motion and unbounded noise, I basically can't get my papers published because they say that I'm an amateur. I don't know what I'm talking about. I don't know if you do epidemiology or something like that, why boundary motion should really be essential noise in their models. Anyway. Good. So I talked a little bit about motivation of bounded noise. What's the pros and cons? So the pro is that I think it's natural in some settings, and some dynamical features can be expressed. For instance, trapping regions. You really have some regions, you can identify them, you can talk about them. If you have unbounded noise, you can try to say, well, maybe there's some region, give a look at the invariant measure that it looks like you're lost in some region, but maybe not always. The cons, of course, is that there's a lack of mathematical theory somehow. So this is where you bump into. You say, well, you can run something on a computer, but no one tells you what you can say. You cannot really use tricks in stochastic analysis because it doesn't really work. You can, of course, use operator theory, and you can try to do numerical stuff and so. But there's also lack of the shelf computational tools sometimes for these things as well. So you can't really maybe do everything so smoothly. So what I like to look at is these trapping regions. So how can you look at these trapping regions? You can think, for instance, as a dynamical system, generated by all noise realizations, but I'm not looking at pushing measures forward. I'm just looking at the regions where I can up. So I'm going to look at the topological model of the random dynamics, and that's the set value dynamical system. From one point you go to a set, and from the set you go to another set, and so on and so on. Now, if you have an invariant set for this system, and for instance an attractor and so, then you will typically have that such a set is a support of a stationary measure. Yeah, so these attractors of the set value systems are some kind of a topological aspect of things that also have probabilistic things. But the advantage of doing this topological theory is that I can forget about probability theory for a while, because I just look at some kind of like transformations on the set of compact subsets of some space. Now the problem a little bit is that this set of compact subsets is a very nasty object, because there's so many, it's infinite dimensional obviously, but it's also really rough, and there's not much you can do actually in terms of analysis. So set value dynamical systems are nice to define, sometimes very hard to work with. So how can you work with such a set valued system? But you can of course compute it with some things and so on. And so I want to talk about basically the aspects of how to think, how you can maybe approach such bifurcations of this invariant set. So first look at an example. So look at the Arnold circle map, some invertible map, and I take some noise value alpha here. Alpha will be in minus epsilon epsilon. In simulations, I would take it IID, but it doesn't matter actually, because it's just a topological thing. Only what's important, what is the support of the measure. Good. So what I can draw now is I can draw these pictures, and I can draw, so usually in one-dimensional dynamics we draw a graph, right? And we look at the diagonal and we basically look how you iterate. But now we have an interval because we go from minus alpha to alpha. So you can actually draw the upper graph and the lower graph, and this will tell you all noise release, all possible dynamics. So I start the initial condition here, I look here, then so I end up somewhere in the middle of this behavior here. Yeah? So you can see here. So what happens? You can actually see here what the invariant regions are because you can actually look at some intersection of upper graph and lower graph, and you see that if you start in these little regions here, you always stay here. And here with some simulation, you see some stationary measures. It's nicely in these regions. It's period 2 orbit for the original system, and this is the second iterate for this Arnold map. Okay, but if you then change the parameter, then somehow these curves somehow become detached from the diagonal. Now you can suddenly jump everywhere. Remember, you can jump at every point between the red and blue curve. So obviously you can jump everywhere. So you have a change of the behavior. So where's the bifurcation point? Bifurcation point is when you're just tangent. Yeah. Your tangency, it's your tangency because if you're on one side, you have a bounded region. If you're on the other side, you open up a gap and suddenly you can do everything. So here you see the set. And then if you open it up, then you have the whole set here as an attractor. Suddenly you can go everywhere. So the support of the stationary measure will then be everywhere.
Can you make it locally non-invertible? Like right
well, I do everything here invertible. Yeah, okay. Just keep it easy. As you say, it has to be able to be taught in an undergraduate class. Now, this can be taught. Okay, now the interesting thing is that there is something about, so why do these things break up? How can you think of that? You can actually think of this as a collision between attractors and repellers. So there is actually some kind of definition of a repelling set, which is not the usual definition, but something similar, where you can see that actually these bifurcations of the sets, which are discontinuous, come because you have some kind of collision between these kind of sets. Yeah, so there's some kind of like idea. So we wrote some paper about this some years ago. And yeah, there's several aspects of these things that are interesting. Now in the one-dimensional case, this is very easy. So, you took not so long for us to kind of figure out how this works. So the invariant sets are always bounded by fixed points of the upper or lower map in the invertible case. So that's kind of easy. But now let's look at the two-dimensional case. It's a little bit more different. So in the two-dimensional case, we're now going to map, and we're going to do an iteration, and then we do a ball. And then you do a ball, and you do a ball. And so you get this kind of system. So what you see here is already, you get more interesting shapes. You don't have just intervals. You have actually some things which is extensive. And the question is like, how can you understand the behavior? So things, if you have an invariant set of this type, I don't know what happened here, somehow. Okay, so you can have some kind of invariant set of this type, which is now invariant under the set. So this is the set value. So you map the point, you take the epsilon ball, the closure, and so if the set is invariant, then we have a fixed point of the set value system, and this will then be an interesting object. And then if you change parameters, you want to ask, like, how does this object changes if you change the parameters? And can it also explode or something like that, like we saw just before? Good. Oh. Well, here's a movie. I can't stop it. And this is Henon map with additive noise. And we just changed the parameter in the Henon map. And let me see what is what. So the red picture, oh, I don't want this. The red picture was the attractor, is the invariant set. The black region is the basin of attraction. And the white regions are basically some kind of repelling sets. Yeah. So the problem is, like, how can you actually understand these shapes? I don't know if I can go back here because it seems to be very difficult. It just keeps flipping by itself. Okay, I'm not in control of this computer, apparently. This is not good. I want to really go back to the previous page. Can I do that here? See, it just keeps doing tricks with me. Oh yeah, I can go back. Good. Yeah, so let me just kind of properly say what I wanted to say here, because I was flipping over. So the problem is, like, what are the shapes of this trapping regions? And we had a PhD student work on that, Kalle. What kind of bifurcations can you have, and can you actually path follow these things? Can you actually compute things that you can actually continue these sets? This keeps doing it automatically, I don't know why. Good. So the continuation is very difficult because in this space of compact subsets, this is a really unpleasant space to do that somehow. You can't really use some kind of implicit function theorem or something like that. You really don't know how to do that. Yeah, so then let me now kind of make a comment about this picture. So here you see the parameters changing. This has some characteristic shape. It looks pretty smooth. But sometimes there's some non-smoothness points seem to also appear. So it's something which, and then there's discontinuous changes, as we also saw in the one-dimensional case. Now this simulation is like done by Gaio or something similar. And so the question is like, what can we do? And it turns out that there's a way of actually of doing this with a so-called boundary map. So instead of actually trying to try the set, you try to kind of follow the boundary of this map. And it turns out that this boundary can be formulated as an invariant set of an associated dynamical system on the normal bundle of the phase space. And what you see now is that I can characterize these sets by, I can find this boundary. So this boundary is actually the projection of an invariant manifold of a finite dimensional but high dimensional system that I can follow. And it keeps flipping over. Okay. Yes, I'm not going to tell you exactly how this works, but what I want to tell you is that it's actually possible to follow this. So it is actually possible to use finite dimensional dynamical systems methods of following invariant manifolds or following the points that have invariant manifolds to make up a boundary to really do this very high dimensional problem, which is very nice because actually we can do that because we know already how to do that. We have bifurcation software and so on and so on. So in simple cases, you can do this. Here there's another case what happens, and you see here the bifurcation happening. Here some kind of new manifolds open up, and here you see the repeller, but you see the repeller is a bit late. So Gaio saw it much later than our dynamical system. So it's actually better and also more precise.
Why can't your boundary be fractal?
No.
Because it's special realization.
Because we have balls. Actually, we do convex. Actually, for convex sets, we did something similar, simple with the thing, but that makes the geometry nicer. Of course, general systems are horrible, but why make things generally horrible if you can make it a little bit easier? Now, what happens here?
The compact balls, they form a Banach space.
Yeah, but you know, in order to do any kind of set value analysis which is reasonable, you basically need to do convex sets, and these sets are non-convex, so you can really not do. It's very difficult to do non-convex sets in any reasonable way. People tried, yeah. So it's a difficult problem, but this is a nice way. At least for of course, if things get very complicated, these methods also get complicated. So these pictures, but you see that we have good control over these things, and it's interesting. Behavior, and we can try to track these kind of bifurcations by properties of instabilities that are on the boundary of these sets that can be tracked by this boundary map. Good. Next topic I'd like to talk about is conditioned Lyapunov exponents. So one thing that there's a problem I think with systems with unbounded noise is that we can go everywhere, and maybe we want to have more localized properties. But if I have a Lyapunov exponent or so, it just basically says overall over the whole domain of stationary measure, what is the average behavior? And this doesn't seem to like this. Okay. Good. I need to try to get rid of this. Yeah, so there's a problem with the this bounded behavior, and I will switch now to this. What happened here? Oh, wait a second. There's something gone wrong here. Yeah, there's some problem with the lack of locality in some sense. Oh, what I'm doing. Can I do full screen? Or I don't know where it is. Here on the bottom, yeah. Okay. So the idea is the following, is that one way to get localized phenomena is basically have bounded noise, because you can maybe stay bounded. Another way is to try to kind of think of, even if you have an SD and unbounded noise, maybe you want to restrict the dynamics that actually stays in a region. So for instance, if you're an almost invariant region or something like that, you might want to say, well, what is the dynamics restricted to a region? Or can I compartmentalize the dynamics in different regions in such a way that I get more insight in what's going on? So I will just illustrate this kind of with an example. So here's the so-called system that comes from the so-called Boutin bifurcation. It's basically something where we have two limit cycles. We have a repelling limit cycle, attracting limit cycle, and an attracting equilibrium. And we just look at an SDE where we then have some kind of additive noise to this. And you can, for this system, also do the usual calculation. This is the potential, and then there's here the stationary measure. Has a certain shape like this. And then we're interested now in a conditioned Lyapunov exponent that basically tells us what happens in the inner region that's defined by the unstable limit cycle. So why I'm interested in that, because it's going to tell us something. And so the important thing here is that somehow we can now define a dynamics which is now conditioned on non-escaping. So we don't like escaping. So we have some kind of stopping time in the system, and we try to define dynamics based on things that are not escape. So there is some theory about that, which so-called quasi-stationary distribution, that says basically, well, you have some measure sitting in this set. Of course, it leaks out because you actually tend to, but you can basically normalize every time. And sometimes you get basically stationary behavior of this thing. So you have the measure leaks away, but you can compensate for that. And then we have a stationary measure for the conditioned process. And there will be also some escape rate, which is just related basically to some eigenvalue of some linear operator there. Yeah? But more interesting for our purposes is that there's also some ergodic theory for these kind of things. But it's not the quasi-stationary measure that's important there. It's so-called quasi-ergodic measure. There's a slightly different measure than the quasi-stationary measure, which will have the property that if I look at the conditioned process and I look at observables and the time averages, that will actually converge to the space average over a certain measure, and this is called quasi-ergodic measure. Now, the theory of quasi-ergodic measure is somewhat limited. So there were quite a few people that work on this, but the problem is that many random dynamical systems where you work with, it seemed to be unknown whether there exists actually a quasi-ergodic measure. So with Mateusz Manzato and others, we've been working on that.
What do you mean precisely?
So what I mean precisely?
By quasi-ergodic?
A quasi-ergodic measure is a measure so that this holds. That if you look at the conditioned averages of things, that this converges to the space average. So such a measure, if it exists, we call it a quasi-ergodic measure. Yeah? Now sometimes the quasi-ergodic measure can be described as a density over this quasi-stationary measure.
So what's the tau there?
Tau is the stopping time. It's time that you reach the boundary. So I look at the process conditioned on the fact that I don't escape. So as soon as I hit the boundary, I basically stop and I throw things away.
Yeah, in the case where you have the density, there is a density.
Yeah.
Is this density the fixed point of some operators?
Sometimes yes.
Okay.
Yeah. But this measure itself not. That's right. Yes, under some conditions, it was the whole game somehow. So there's some papers by Mateusz here, and also some paper that we're writing at the moment, where this is done. But what I'd like to emphasize on the fact that so there is this theory. The problem is that it's not always known if these measures exist, but you would hope that they exist because it seems to be natural that they should exist, but maybe not with all the nice properties that you like.
So is eta the leading eigenfunction of the Markov process? The linear operator representing the Markov process?
No.
Why not?
Well, there's actually no.
I mean, because, well, I guess we have the discussion session after. So
Yeah. This is there is a lot of stuff here somehow, which I don't talk about by choice. Otherwise, I spent only talking about that. Good. So now I want to show some. I know. Let me see, where is this thing here? What's going on here? Okay, so here I want to show this simulation. Here's a simulation of two-point process. Oh, it has some problem with my computer, I think. Okay, here's a simulation of two-point process with about one bifurcation. So in this case, the condition of the Laplace exponent is here computed the so-called Q process, which is basically a process that is conditioned on non-escaping. And so it has a negative Laplace exponent inside, but it has actually overall positive Laplace exponent. So as long as you stay inside, there's two initial conditions with a little time lag, stay very close to each other. You basically see only one little worm drawing around. But when you go outside, you will see quickly that it starts separating, because actually the positive Laplace exponent only picks up outside. So it's actually inside this disk, you're basically contracting, but only when you get outside, you pick up this expansion somehow. So it depends on some kind of coordinates. Just an example of how this conditioned Laplace exponent, which is defined here just for the principle here, tells you something about the dynamics.
How is it choose that way, right? To stop?
I'm nearly going to stop, yeah. Okay. Good, there's some other things that I wanted to talk about. You can ask me about it, for instance, in the questions. So one thing is actually talking, for instance, about this how you can use random systems, for instance, to describe hub dynamics, two coupled hubs in a network. You can sometimes, you can use this idea that you have a mean field. You can actually think of these fluctuations as a real random perturbation, and you can compare the real network dynamics by the random dynamical system, and you can show that actually the random dynamical system is a very good model, also far away from the limit where the mean field reduction works. I think that's another useful area. So we did some work with Jaroen Lamb that unfortunately now I'm not showing. So I apologize to Jeroen if he's online that I didn't get to do it, but we will write a paper about it, so you can see that later. So apologies for the delay. Okay, thank you.